Hello everyone. In this video I am going to explain the Microprocessor 8085 based assembly level program particularly for subtraction of 8-bit number from one 8-bit number to another 8-bit number. Then I'll explain the program for the subtraction of one 16-bit number from another 16-bit number. Then I will do the multiplication of one 8-bit number with another 8-bit number, then division of one 8-bit number by another 8-bit number. Okay, so let's start. Okay, let's start with this assembly level program for the 8-bit subtractions. That is the subtraction of 8-bit number from another 8-bit number. So the minute means from which you are subtracting. Suppose 7 minus 5, where 7 is your minute and your 5 is your subtrahend. So from the minute is supposed stored in 2050 memory location, and say your subtrahend is stored in your 2051 memory location, and say difference, the result, is stored in 2052. Okay, so for the minute which is stored in 2050, so what we can do is, since all are consecutive memory, so we can use the instruction, say we can use the instruction LXIH. Okay, so let us start with this LXI. So here the LXI H. Okay, so LXI H will load the HL register pair with the memory location or the data given, that is say 2050. So this is for this instruction is for your the first data. I mean this the first data, that is your minute, is stored in your 2050. Now I am moving that 2050 to the HL register pair. Now as you know, in case of addition as well as in case of subtraction also, the first number, I mean the minute, has to be stored into the accumulator. So it is always subtracted from the accumulator. So therefore the first number, that is the minute, should be stored into the accumulator. Now where is the first number? The first number, that is the minute is in the memory location 2050. Now that 2050 location I have stored in HL register pair. So from the 2050, whatever be the data, that is your minute, now I am copying to accumulator. So for that, move A comma M. So by this instruction, the first data which was, that is the minute, which was stored in 2050 memory location, now copy it to the accumulator. So next you just increment the HL register pair. So by incrementing INX H, that means incrementing HL register pair by 1. So now HL register pair becomes 2051. So once it goes to the 2051, now your M is 2051 memory location. So in the 2051 you have already stored your subtrahend. Okay, so then we can use the instruction for the subtraction directly, that is your SUB. So SUBM. So what SUBM will do? SUBM is your the subtraction of from the accumulator minus the data stored in the memory location whose address is in HL register pair. So that means this means your accumulator will be loaded with the result is stored in the accumulator. Okay, so the result means the subtraction from the accumulator, and the data is in to the memory location whose address is in HL register pair. So what is the in the HL register pair? That is 2051. So whatever be the data stored in 2051, that gets subtracted from the accumulator. Okay. Then After this subtraction, the result is in accumulator. So what you can do is simply again INXH. So this INXH will make HL register pair 2052. So once this INXH is executed, that means your HL register pair get incremented by 1. That means now it becomes 2052. So HL register pair is 2052. So your M is now 2052. So simply your move M comma A. So the result is now stored in your 2052. That is the difference, and that's all. So okay, to stop. So that's all for the subtraction of any 8-bit number from another 8-bit number. The minute is in the memory location 2050 and the subtrahend is in 2051. So therefore 2050 first I have loaded in HL register pair. So then this 2050 memory location can be considered as M. So from that M I am copying the data to the accumulator. So because it is always subtracted from the accumulator, then INXH will make it 2051. The HL register pair becomes 2051. So therefore now my new M will be 2051 memory location. So directly in the 2051 there is already your subtrahend is there. So sub M. After that sub M, and after that this subtraction, this result is now stored in your accumulator. So again I further incrementing HL register pair. So once you further increment the HL register pair, then your HL register pair becomes 2052. That means your M now becomes the memory location 2052. So where I am storing the result, move A comma M comma A, and then finally halt. Okay, now we will see the 8-bit decimal subtraction. Okay, so this 8-bit decimal subtraction for this 8-bit decimal subtraction. So subtraction of 8-bit decimal number from another 8-bit decimal number. So again, suppose the minute is stored in 2050 and your subtrahend is in 2051 and the result is in say 2052. So now here one thing, this is the program. Okay, I will explain the program. So thing is that since it is decimal, that means the BCD, and as you know, for the BCD arithmetic there is the instruction DAA, the decimal adjust accumulator, but there is a point, there is a consequence of this DAA instruction. So this DAA instruction is applicable only for the addition instruction, that is for ADD or ADC, but this the DAA instruction will be not applicable if you are using subtraction instruction, say SUB or SBB, subtraction with borrow. So that means DAA can be used only after, immediate after the addition instruction like AD or ADC, ADD or ADC. So therefore while doing this subtraction of decimal number, we should follow the method of complement. As you know, say in case of binary subtraction, we use the method of 2's complement subtraction. That means suppose minute minus subtrahend. So in the method of 2's complement, what we do in case of binary number, what we do? We do the 2's complement representation of the subtrahend, then we add it with the minute. Suppose the x1 minus x2 in case of binary. So what we do? Minus x2 we represent it in 2's complement form. Then that 2's complement form of minus x2 is get added with the x1. Similarly, in case of the decimal number, what we do is we use 10's complement. So suppose your 56 minus 24, for example, 56 minus 24. So where 56 is your minute, 24 is your subtrahend. So in this method of 10's complement subtraction, what we do, that minus 24 will be represented in 10's complement, then it will be added with 56, and the result is the subtraction of 56 minus 24. Okay, subtraction of 24 minus from 56. Okay, so that is why what I do is first the memory location for the subtrahend, that is for example say for example, you are going to subtract x1 minus x2. So here this x2 is your subtrahend, that is your subtrahend, and which I am going to represent in tens complement form, that is minus x2 in tens complement form. Then that tens complement of minus x2 will be added with x1. Okay. So my minute subtrahend is in the memory location 2051. So that therefore I have loaded the HL register pair with the 2051 memory location. Okay. So now in HL register pair 2051 memory location is stored. So therefore my 2051 memory location is M, capital M, because M is the memory location whose address is currently in the HL register pair. So then for the tens complement, as you know, 9 minus 1, 9 minus that plus 1, okay, that is the tens complement. So that is your 9's complement plus 1. 9's complement means subtracting each and every digit from the 9. Okay. So now I have loaded accumulator with 99 because it is 8 bit, that is why 99, otherwise it is 0, 9 or only 9. So MVI A, 99. So this 99 is now there in your accumulator. So therefore sub M M means the memory location whose address is in 2051, whose address is in HL register pair. So what is there in the HL register pair? 2051. So what is my M now? M is the memory location whose address is in HL register pair, that is your 2051. Now what is there in the 2051? My x2 is there. So therefore sub M means 99 minus x2. So it is 9. At this point your 9's complement result of x2 is in accumulator, because this is the after this instruction result is in accumulator. Then simply if I increment the accumulator, so 9's complement plus 1 INR A. So whatever be the result obtained at this stage which is there in the accumulator, then INR A it will added 1. Okay, INR means increment by 1. So accumulator content get incremented by 1. That means at this point it was 9's complement, then INR A means it is 10's complement. Okay. So my minute subtrahend gets to the 10's complement, and right now that is there in your accumulator at this stage. So then what I did is DCXH, instead of INXH I am using DCXH. DCXH means it will decrement the HL register pair by 1. So what is there in the HL register pair? 2051. Now it is decremented by 1. So decremented by 1 means it becomes 2050. So now what is my M? M is the memory location whose address is currently specified in HL register pair. So what is the currently HL register pair is holding? 2050. Now what is my 2050? 2050 is my memory location for the minute, that is x1 is now in 2050. So at this point M becomes 2050. So simply add M. So what is there in the add M? Add M means it will add the content of the memory location whose address is in HL register pair with the content of the accumulator, and result is placed in the accumulator. So accumulator is holding the tens complement of x2 minus x2, and HL register pair is holding 2050, and 2050 is holding my x1. So it will add x1 with the 2's complement of minus x2. Okay. So it becomes the 2's complement method of subtraction. Then I simply use this the, because as I mentioned this DAA instruction is applicable only immediate after the addition instruction, not for the subtraction or any other instruction. So therefore I use this the. So this the will make the result decimal, and finally I have stored it. Okay. So here I can use INX, but I have to use, because since I have used this DCX over here, so therefore if I use the DCX means it becomes 2050. Now if I would like to use the INX, so I have to use INX twice. So INX then move M comma A. So it becomes 3 bytes. So better we use STA directly 2052 and stop. Okay. So this is how we do the decimal subtraction. Hope you understood. So now I am going to explain the program for the 16-bit subtraction. So subtraction of any 16-bit number from another 16-bit number. So the minute, that means from which the number is to be subtracted, is stored in say 2050 and 2051. Because it is 16-bit, we need two memory locations. So 2050 is holding your lower byte of the 16-bit number, of my node, and 2051 is holding the higher byte of the 16-bit number, and the substrand that is to be subtracted is stored in 2052 and 2053. That means 2052 is holding the lower byte of the substrand, and 2053 is will store the higher byte of the substrand, and the result is stored. Result is also 16-bit, so therefore result is stored in 2054 and 2055. That means 2054 will store the lower byte of the result, and 2055 will store the higher byte of the result. So now since it is 16-bit, so obviously we will use the LHLD instruction. So what is LHLD instruction? So that means first, because it is in a 16-bit, so what we will do, we will use the HL register pair only, okay, for that. And although there is no direct instruction for the 16-bit subtraction as like addition, there is an instruction for the direct 16-bit addition, which is the DAD, but there is no such direct instruction for 16-bit subtraction. So what we do is we divide we'll subtract first the lower 8 bit of the substrand from the lower 8 bit of the my node, then we will do the subtraction of the higher 8 bit of the substrand from the higher 8 bit of the my node. Okay. So for that, since I am going to use this XCHG, as you know, this XCHG will exchange the content of the HL register pair with DE. So that means this number, whatever be the number stored in HL register pair, will now go to DE. That is why I have first used the memory location for the substrand. Okay, so 2052 and the 2053 is the memory location for the substrand. So LHLD 2052 means L will be loaded with the data from the 2052, and H, that is the higher byte of the register pair, will be loaded with the data from the 2053. So that means my substrand, that is the data to be subtracted, the substrand is now in HL register pair. Lower byte is in L, higher byte is in H at this point. Now after that I am exchanging, because there is only one instruction to load HL, that is LHLD only. So then I am using XCHG. XCHG means it will exchange the content of the E with the HL. So that means whatever be the content in L, that goes to E, and whatever be the content in H, that goes to D, and E goes to L, D goes to H. But I don't know what is there in the DE, and which is not our concern. Okay. So now HL is now the content of HL, that is my substrand, is now in DE register pair at this point. So again I am using LHLD. So HL register pair is now loaded with my node. So 2050 and 2051. So from 2050 data goes to L, from 2051 data goes to H. So which is my node. So now my node is in HL and substrand is in DE pair. Okay. My node is in HL, substrand is in DE pair. Now since there is no such direct instruction for the 16-bit subtraction, so I have to do it 8-bit. So what I did is, from L, so what is there in the HL? HL is loaded with my node. So therefore that as you know, the subtraction instruction always does the subtraction from the accumulator. That is why the lower byte of the my node, which is there in L register, is now copied to the accumulator. Okay. So lower byte of the my node is now copied to the accumulator, and lower byte of the substrand is already there in the DE register pair, in the E register pair at this point. So SUBE. So that means this means A minus E. So A is now my lower byte of the my node, E is now having my lower byte of the subtrand, and after this the lower byte of the result is in accumulator. Again I am copying that accumulator, that result, lower byte result, into the L. Okay. So similarly after that goes to the higher byte. So higher byte is in H, higher byte of the my node is in H register. So I am now copying the higher byte of my node to the accumulator, and lower byte of higher byte of my substrand is already there at this stage in D register. So SBBD. Now it is not SUBD, it is SBBD. Hope you know SBB. SBB is subtraction with borrow. SUB means it does not consider the borrow, because you can imagine this lower 8 bit, higher 8 bit as one column, second column. Okay, so in the lower 8 bit, while subtracting the lower 8 bit from the lower 8 bit of my node, there may be a borrow generated. So therefore, while subtracting the higher 8 bit of the subtrahend from the higher 8 bit of the my node, we need to consider that borrow. So therefore, the instruction instead of SUB, it is SBBD. So that means it is A minus D along with the borrow. Okay, and the result is in accumulator. So again I am copying that result into the H cell. So H, okay, A to H. So therefore, my result is now lower byte is in L, higher byte is in H. Okay. So finally I have stored this SSLD storage. That is why actually I have copied here this lower byte to the L and higher byte to the H, because I am going to use this directly to store. Otherwise also you can store separately. Okay, so because I am going to use this SSLD, that is why I have copied these two things. Okay, so SSLD means it will store HL register pair to the 2054 and 2055. So 2054 will store my result, lower byte of the result, which is there is in L now, and 2055 will store my higher byte of the result, which is there in H now. Okay, so accordingly it serves the purpose and stops. Okay, hope you understand. So hope you understood this program for the subtraction. Okay, thank you for the listening.